This is Hita the Explorer. She'll tell us about explorable theorems. Sorry, I know.
Great, thank you, Josh. Yes, okay. So math is hard, and in particular, it's hard to read. Consider this theorem, and the details are unimportant here, but basically it's saying that finding a balanced split of a graph is hard. Like, it's really hard. It says NP complete. So if a mathematician or anyone were to read this theorem, they'd have a few questions, namely, what does a valid split look like? And why is this problem computationally hard? And in what cases is the problem actually easier? These are examples of questions that people actually do ask when trying to understand math. And so I tried to answer one of these questions. I wrote out a small example graph and tried to find that optimal split. On my first attempt, one of my splits was invalid, it was too big. On my second attempt, it was suboptimal, I had too many splits. And then by the third time, I kind of got it. Again, this is a process that people actually do in order to effectively read proofs. While there are a lot of people who still will write things by pen and paper, a growing number of people use chatbots to understand math and explain it to them. And what happens here is you're basically reduced to two actions. You type out a question and you read an answer. In contrast, when I wrote things by hand, I was able to work out examples and subsequently form a high-level understanding of the proof intuition, understand low-level details, and then ultimately be able to use the knowledge that I learned and apply it to new context. So it's a very active process. So here we ask, how can this passive act of proof explanation become more active and feel more like proof exploration? So towards this, we present Explorable Theorems, which is a system that allows readers to tinker with formal statements and their proofs with explanations that are mostly formally backed. So we'll talk about this first part first. Consider this simpler theorem, which states that for all integers, if x is greater than 2, then x squared minus 1 is not prime. So if a reader were to get a high-level understanding of the statement itself with explorable theorems, what they could do is see how different values of x actually play out in the proof predicate. So you can, in the theorem predicate. So you can see for values x greater than 2, the theorem holds. For values x less than or equal to 2, sometimes the theorem holds and sometimes it doesn't. And if the reader were to dig deeper into this, they could work out the proof on particular examples. So below each step of the proof, there's like the math is worked out below. So here one can see that for values x greater than 2, that number n, x squared minus 1, is actually composite, like 24, 15, 8, these are composite numbers. And then for values x equal to 2 and negative 2, n is prime, it's 3. So at this point, a reader probably knows that there's something going on when x equals 2 and negative 2, such that the proof doesn't pan out, doesn't work. And so if they wanted to dig a little more deeper and understand the meanings of terms and statements, they could do the following. So let's say they're reading through one step of the proof that says, we show that s is greater than 1 by the following reasoning. X is greater than 2, so x plus 1 is greater than 3, so s is greater than 1. Well, reading this, I'm sure one would want to know what s is and why we care that it's greater than 1. So a reader could click on this step of the proof, and they could see the following. So first they could see that s is defined as x plus 1 in an earlier step of the proof. So this is one of the factors of the number that we're trying to prove is composite. And then later on in the proof, we can see why this matters. So ultimately, we want to show that n has a factor s such that s is greater than 1. And this makes it a lot more clear why, when x is equal to negative 2, the proof doesn't hold, the theorem doesn't hold, because s is not greater than 1, and the proof step breaks. So in these ways, with explorable theorems, a reader can form a high-level understanding of a theorem statement, work out the proof on examples, and also understand the minutiae of the proof, like meanings of terms and statements. So now let's talk about these explanations that are mostly formally backed. We're going to start with a natural language theorem and proof. We assume this to be human written, so assume that it's correct. And then we use an LLM to generate its lean counterparts. So lean, for those who are unfamiliar, is basically a programming language and an interactive system that allows one to write machine-checked proofs. And so if we're able to write something in lean, we can assume that it's correct. So consider this theorem again. Let's say the first step of the proof is denoting x squared minus 1 by n. And in lean, that would be written like this. So now we take each step of the lean proof and we clone it with a couple of key differences. One is we set specific values for each variable. So here x is set to 5, and n is expressed in terms of that x. So now let's keep track of the proof state. Here we have x equals to 5, and n equals x squared minus 1. Then what we'll do is we'll substitute that x equal to 5 back into n. And so x squared minus 1 becomes 5 squared minus 1. Then we simplify this expression, so 5 squared minus 1 becomes 24. And then the proof kind of vacuously follows because we know that 24 is composite. Then we dump all of these intermediate proof states directly into the interface so that a reader can see like 5 squared minus 1 equals 24 and enable interactions like these. Next, another thing that we do is we take each step of the lean proof and we build this dependency graph to see what tactics or facts rely on other facts. So for example here, n is defined by mdef, which is x squared minus 1. And so if a reader were to click on a particular step of the proof, they could see, 1, what fact is being defined, and 2, where those facts are being used later on in the proof. So in sum, lean exposes the proof state and dependencies, which we turn into interactive, formally grounded explanations. So here are some questions that I have for the group. I'd be interested to know like how it sits when I say that this system is formally backed. And I also have been curious to know, like, beyond verification, like beyond hallucinations, what is the utility of integrating formal methods into LLM interfaces? Because my instinct is that, like, LLMs are really good at certain tasks, but there's still some inherent benefit to integrating these formal methods. And then lastly, I'd want to know, beyond education research, where interfaces like these could be applied, like maybe in high-stakes decision-making, like law or something like that. So yeah, I'll stop there and happy to take any questions. Thank you.
Brave first person.
So this is super cool. The thought that I had while you were showing the like x squared minus 1 example was like, I didn't actually see the full proof, but I'm assuming it's like a constructive proof where it's like you can prove that therefore you can factor into x plus 1 times x minus 1.
Exactly.
And therefore the visualization would show like for the yellow or for the green region it would show like this is composite because, and then show those two factors, right?
Mm-hmm.
So I guess I was wondering, like, in general, like in lean, you can write non-constructive proofs. Like, this is kind of like one thing that differentiates it from earlier proofers is like it lets of a focus on constructivity. But for the kinds of math that you're envisioning, do you see it as like largely the proofs are constructive? In which case, like the visualization that you can show can take advantage of that constructivity, or maybe not so much.
Yeah, that's exactly right. So I think short answer is yes. Long answer is yes because. Also, we're able to very easily mirror the natural language proof and the lean proof if it is a constructive proof. So it just lends itself to a lot of useful interactions that we can still claim to be formally backed that we kind of lose out on in other cases. Mm-hmm.
Really fantastic, interesting stuff. This makes me really curious. You showed the example of like a number line as a way to climb the ladder of abstraction and see like the space of all possible numbers. Mm-hmm. How do you see the space of all possible graphs or the space of all possible groups or like more complex objects?
Yeah, that's like the perfect question. So I feel like I might not have to think about that for too long because I feel like lean doesn't work that great with graphs. But if it were, we could use tools like drop downs to see like denoting however many vertices we want, however many edges we want for a graph. There are different ways that we can like characterize different inputs. So maybe instead of that being discretized in a number line, it could be something that we construct as a user. Actually, in the tool, this is something I highlighted. You can also specify your own input value to test the theorem on. So maybe that's something that we would rely on in those cases.
like the idea that you have this theorem, and the thing that you're visualizing is actually examples that don't satisfy the assumption of the theorem, sort of like nearby territory.
Mhm.
I'm having trouble formulating a question, but like, I guess it's a similar sort of how do you generalize this to other cases? Is there a systematic way of coming up with what the nearby cases are?
Yeah, good question. So what we do is we take the theorem's assumptions and its predicates, and we basically we use like Lean's QBT, is it plausible, to generate a bunch of random inputs.
Okay.
We see we see whether these inputs satisfy those conditions or not. Cool. Thank you.